So this was a structure pop quiz 13. Can mention your doubts. Question number 1, any doubt? The question was related to work, energy, and power. Work done. Any doubt in question 1? Question 2, any doubt? No doubt. Question 2. Okay. Question 3, any doubt? Question 3. Okay. In question 3, a student carried out an experiment to determine the viscosity of washing up liquid using the apparatus shown. So student want to determine the viscosity. What's a form? Viscosity is a property of a fluid to resist the flow. When the fluid resists the flow, we call that as a viscosity. How we can work out the viscosity, the formula for the viscosity. So that is 2, the difference in the density of object and the fluid. Density of an object minus density of the fluid, R squared G over 9V. That's how we work out the viscosity. Now, practically, like whenever we are carrying out the experiment, we always prefer to repeat the experiment. The density of the object is constant. We'll have that. The density of a fluid is also constant at a certain temperature. That's a known thing. These are the constants. Gravity is also constant. So what are the main factors here when we relate them by equation? So we can say viscosity will be equals to 2, the difference of the density of object and the fluid, G R square by 9V. So what are the parameters which are variable here? What we can change? We can change the size of the sphere and we will work out the terminal velocity. As we change the size of the sphere, the terminal velocity will also change. So these are the two factors which can be changed. And the independent variable is the size of the sphere, and the dependent variable is a terminal velocity, because different size of spheres will have a different terminal velocities. How practically we can determine the terminal velocity? So what we'll do, we'll place two rubber bands or two markers. Yeah, like you can mark this cylinder. So when this sphere crosses the first marker, so when the sphere crosses the first marker, we'll start the timer. And when the sphere crosses the second marker, we stop the timer, or reaches a second marker, we stop the timer. So we know the time and we'll measure the distance. So distance divided by time, what we'll get? We'll get the speed, the terminal velocity. And the size of a sphere, how we work out the size of the sphere? We'll not measure the radius because radius is not directly measured. Radius is calculated. So using a micrometer or a vernier caliper, we will measure the diameter and use half of a diameter, we'll calculate its radius. So the points you will mention about this, the calculating of viscosity. So what we can do, we can measure the density of the object and the fluid will be known and the gravity is constant. So we'll take a sphere, measure its diameter and find the radius. Same way, we place two markers, one near the top and one at the bottom. And when the sphere crosses the first marker, we'll start the timer. And when the sphere reaches the second marker, we'll stop the timer. We'll measure the distance between the two markers and distance divided by time, we'll get the terminal velocity. And we can repeat this experiment with different size of spheres and take an average. Is it clear? The next we have the experiment to find the speed of a sound in air. The speed of a sound in air can be determined using an apparatus. So what we have here a CRO, cathode ray oscilloscope is there. We have a microphone which will produce a sound, which will detect the sound. We have a loudspeaker which will produce the sound, and we have a scale, a ruler is there. By looking at this setup, what you understand that because if we need the speed of a sound to work out the speed, we need distance and we need time. So how we can measure a distance? We'll actually measure a distance between the loudspeaker and the microphone, which is detecting the sound. And how to work out the time? This is a two beam oscilloscope. Like it is when the loudspeaker produces a sound, it will give us one peak. And when the microphone detects the sound, there will be another peak. Why not V equals F lambda? Because we don't know the frequency of the sound and the wavelength. Like it's not producing a standing wave. That's why we cannot use V equals F lambda. If it was producing a standing wave, yes, we can use V equals F lambda. But here there is no standing wave. It's actually what happened. A speaker will produce a sound and that sound will travel towards the microphone and microphone will detect. So what actually happened here that when the speaker produces a sound, there will be a peak. When the microphone detects the sound, there will be another peak. And how we can determine the interval between the sound which is produced and the sound is detected. So for a CRO, cathode ray oscilloscope, we have this grid and we have the labels also are there. Like example, one division stands for 10 milliseconds or 15 milliseconds or 30 milliseconds. So this is a grid of the CRO, cathode ray oscilloscope. So how many like boxes are there? One, two, and three boxes. And let's say that the time one division stands for 10 milliseconds. So if three boxes are there, so we'll multiply by three. So it means the time taken by sound to travel from the loudspeaker to the microphone is 30 millisecond or 30 into 10 to the power negative 3 seconds. So that's the time. And the distance by using a meter rule will measure the distance and speed is equals to distance divided by time. That then we'll repeat the experiment with different position of a loud by changing a distance between the loudspeaker and the microphone. Is it clear? So that's how a CRO can be used to determine the speed at which the sound travel through the air.